Okay, friends, I don't know who was yesterday here at the lecture of our friend Dьюлы Катоны. Unfortunately, myself, I could not come since I was in a different city. I was in Adige Republic in my COP. So now I am here, and it's a great pleasure for me to welcome Dьюлы Катоны. And today, the event is different from the yesterday's one. So yesterday's one was for lectures. 3 lectures we have. Yesterday's, tomorrow, and Friday. And Friday. And today is a seminar, interdepartmental seminar on discrete mathematics. Okay, thank you very much for coming and for giving us a talk. There are some people who, I guess, don't speak Russian, so it's better to speak English. But it's possible to say some words in Russian as well, of course.
Yeah. Я очень благодарен за приглашение на этот известный семинар, и что могу докладывать среди друзей. Но я начинаю. Oh, I'm sorry. I forgot that I have to speak English. So this is the usual notation for a graph, and I say that a vertex x dominates the vertices y if either it is the same or there is an edge between x and y. In other words, and this is very often called the closed neighborhood of x, and this is the notation. So the vertex itself and the neighbors. And I give an example. So this is the graph. This is a vertex. Then this is the neighborhood. So these vertices, these 3 vertices, and it's x itself. And we call D, which is a subset of the vertices, a dominating set in G if the union of these closed neighborhoods of the vertices in D give all the vertices, the total set of vertices. So it means that for every x, either x is in D or there is an edge from this x to the other one. I am afraid I am explaining too much this easy concept. Turning back to the example, if we take this vertex and this vertex, this one dominates these 4, this one dominates these 4, but these 2 are not covered by any of them. So this is not a dominating set. We have to take both of them because they are not adjacent. So these 4 vertices dominate the graph. So this is a dominating set, and the domination number is the smallest size of a dominating set, denoted by gamma g. So our first trial was very weak because these 2 vertices dominate everything. So all vertices, including these ones and everything. So the domination number of this graph is 2. Now I define the subject of my lecture. It will be a bipartite graph, where here we have k-element subsets. So one vertex corresponds to a k-element subset of an n-element set. I will use this notation for the n-element set. And I hope it is clear. So this notation means that all k-element sets of an n-element set. And here I have the l-element sets, and two vertices are adjacent if this is a subset of this one. I don't understand this. Finished. Oh, yeah. So the hopeless, fearless goal is that try to determine the dominating number of this graph in general. And I start with a very modest result. When this is 1, so if here in this picture, it means that we have here the elements. One element sets are elements, and here the k element sets. Oh yeah, thanks. Now it works. and we with a lady from Iran, we determined this value, and the construction is the following. Take one k-element set here out of this one element set, because here we have the one element set, but fix a k-element subset here, and connect one element with all of them. Sorry, and you can see that this is a dominating set. This one here, this is a k-element set which dominates all these elements here, because this is the same set actually. So here it looks like a fat thing. Here it's just a point, but it's the same thing. So this vertex dominates all these, and the other k-element subsets which do not contain this one contain at least one of these elements. So these vertices dominate all the other k-element subsets. And the number here, m minus k red dots here, plus this one here. So this point and these are a dominating set. And it's actually, we had a fairly complicated proof. And again. And Joel Touza noticed that there is a trivial proof. So it will be a joint paper with him. And yeah, so we then next step was when L is 2. And so we made a conjecture. I will explain later why we conjecture this one because of some constructions, but the constructions are not so easy that I could show immediately just one by one. And so this is what we conjecture, that it's n squared, constant time n squared, and some rest, something which tends to 0. So it is asymptotic only. So when L was 1, then we were able to determine the exact value. In this case, I think it's hopeless when L is 2. It jumped over. Cannot go back. Yeah. So, so in this case, I hope you believe that when oh, why not we? I know why not. So if we substitute in the formula k equals 3, then we obtain this constant. Oh, you suggest to go there? You. Oh. Oh, I see. It didn't see it. Yeah, that was the problem. I see. Okay, so if you plug in here 3, then it will be 6 over 16, which is 3 over 8. And so in this special case, we had another special case of this conjecture. And now I show the construction for this case. Take a bipartite graph with these 2 parts, so n half. This letter is too small, so n half elements here, and we will have 2 and 3 element subsets all together on the same picture, so it will be a little bit confusing. I suppose that n divides, that 4 divides n, so this will be, n half will be still an even number. The construction works for other values also, but it's easier to show in this case. So take here a complete, so this is a complete graph here. I said bipartite graph it's wrong. Is the so oh, here. So I said bipartite. It's written a complete graph. So here we have a complete graph, and here we have a complete graph, and take a complete matching here. So and this is why we need this, because this should be divisible by 2. So pairs of edges, actually. The edges are already there. We use these edges to construct 3-element subsets in this way, that take one of the sets and add this vertex to get a 3-element subset, and then this one and this one, every one to these 2. So they will be different 3-element subsets, and do it with the next pair of vertices also, and with every one. And so this will be, why is this dominating set? So what we have to show that every edge is either in the graph we started with. The graph consists of the edges in these 2 complete graphs within, and so either everything is either an edge or it is covered. It's a part of a 3-element subset, and on the other way around, if we take a 3-element subset, then it's either chosen or there is an edge which is a subset of it. So in this way, everything is dominated. And so check it why it works in this case. So if so these edges are already in the construction within. So we have to see only these edges. And you can see that we have an edge from every vertex here, because every vertex is covered by this complete matching. And so you can see that we have edges here. So all edges are covered either by an edge itself or by a triangle. And what about the triangles? If you take any triangle in this one, then at least two, because we have two classes, at least two vertices of the triangle or the filament set must be in one side, say here or here, and then this we have an edge which is a subset of the three-element set. And I don't waste time with showing that this will give this number. Oh, I did. So n half choose 2 times 2 plus we have n over 4 edges here, and to everyone we have n over 2 third points. And now you believe me this. But this is only the construction. I didn't show that we cannot do it with fewer. So this is what we had. So let us try to see the case k equals 4. One of the ideas applies here easily, namely, you remember that so when we took a triangle, a three-element subset, then two had to be in one class. And then it is covered by, it's dominated by the edge there. So this part works here also. If k is 4, then a k-element subset must contain two elements, at least two elements in one of the classes. So every 4-element set is dominated by these edges. So this part is easy. It's less easy the other part, that every edge is either chosen, so it's in the one class, or if the edge is here, then it should be covered by a 4-element subset. And these numbers, I don't know if visible, it's modulo 5 are numbered, the elements, so it's n is 15. It's a very special case. And I just give some 4-element subsets. The colors are visible, fortunately. So this two and this and this. So this is a 4-element subset, this kind of brownish 4-element subset. And then we have this violet one. This is again 4 elements. And the green looks like this. So 3 4-element subsets I gave. And they have, one has 2 elements here, one here, one has 2 elements here, one here, and this one has 2 elements here and one here. And now take the cyclic shifts. So we add any number modulo 5 to the construction. And so if you check, differences between these two columns are 0. So this is 0, and this minus this is -1. This -1 is -3. One of them is, yeah, this is minus. Oh, sorry. This is -1, and this is -2. No, something is minus. No, this is -3. This is minus. I don't see now. Okay, so believe me that the differences are all different here. So the modulo 5 in between these two, and the same is true here, and the same is true for between these two, because there's also. And so when we take the shifts, then they will be all different, because so for instance, this horizontal line will be horizontal always. When the difference is 1, 2, 3, then with the cyclic shift, it will be also 3 if you shift it. So all these edges, 5 times, this is 1, 2, 3, 4, 5. 5 times 5, they are all different, which is 25, and we have 25 edges between. So it means that every edge between these two, or these two, or these two, they are covered by this 4-element subset. So it works. I will return to the continuation of this construction, but so now I just come back. Yeah. So what do we get from the what do we get from the general conjecture if k? Oh, it came back. From the general conjecture, if you plug in 4, that will be 7, and that will be 30. So we need this value if the conjecture is true. So it's a special case of this conjecture. And so what we have seen is that when we have 15 points for 2, the dominating number is this. Why? Because we have 3 times 5 over. So in one class, 5 points and 10 edges, and 3 such classes, 30, and we had 3 4-element subsets, cyclic shift. That's 3 times 5, 15, so 45. So when we are going to infinity, it doesn't seem to be very useful, but I have to introduce a new concept, the transversal design, for 3 classes at the beginning. So we have 3 equal classes, like in our construction, and we take 3-element sets in such a way that one is here, one is here, and one is here. It's not like before we had 4-element subsets, and this has only 1 in each one, and we call this a transversal design if all edges are covered. So every pair between these two are covered exactly once. And a theorem, a very old theorem of Hanani, is that if Q is a prime number, then there exists a transversal design. What was So this was Q, the number of elements in one class. So now I continue the construction. Take, so this is 5, this is not S, 5 element sets many times. So it has to be divisible by 5, and then we have altogether 5 times Q elements, and it's divided into S element, 5 element parts. So we have Q, such little bug, and the same here. And make a transverse, since the number of these small ellipsoids is Q here, Q here, Q here. So we can use the theorem of Hanani, that there is a transversal design for when these are the vertices, these little ellipsoids. So these are the vertices, and then we have a transversal design. So one here, one here, one here, and so we know that every pair between these two things are covered. And now we have here this is an edge between these two. If we have such a edge, then replace it with a construction. No, sorry. So we have 3 element sets, right? And we replace this by our construction. You remember it was 5 times 5 times 5 is here. Yeah. Where is it? I lost it. Oh, it was earlier. Yeah. Yeah. So this is 5 elements, 5 elements, 5 elements. And within, so now we have this 3 element subset of these 5 element small sets, and plug in our construction for 15, 5 plus 5 plus 5. And it's easy to see that every edge now in the real graph will be covered, because every edge is between these two somehow, and the transversal design has an edge between these two, and we plugged in our construction, it has an edge between any 2 points of this and this. So now we have a construction for n equals 3 times 5 times q, where q is a prime power. And in this case, the number of edges within the columns. So n over 3, choose 2, and we have 3 such classes. So this will be about 1 over 6 times n squared. And the number of other edges will be, it's easy to see that this will be 1/3 of n squared. And so one 4-element set covers exactly 5 such edges. You remember in the, I go back. I mean this one. So a 4-element set covers this edge, this edge, this edge, and this one. So it covers 5 edges. So this was the number of edges, and so yeah, it's clear because it's n over 3 times n over 3 times 3, and this gives it. But we covered these edges by the 4-element sets, and the 4-element sets had 5 edges, so we have to divide it by 5. So the number of real edges is this. The number of 4-element sets in this, and this is a dominating set. So altogether we have 1 over 6 plus 1 over 15, which is 7/30th. So we have a construction again, like for the case when k was 3, but we don't know from below, so that we cannot have a smaller number of vertices, dominating vertices. So this is what we were able to prove. Now, what happens if k is 5? Of course, we make now 4 classes, and again, when we have a 5-element set, then it is covered by one of the edges, because 2 must be 1 class. The problem is, again, so all 5-element sets are covered by an edge. The problem is to cover these edges between 2 classes with the smallest number of 5-element sets. So we can try again 1 here, 2 here, 1 here, 2 here. With such 5-element sets we can try. And again, if for some r we are able to do it, like for case when k was 4, then we were able to do it when r is 5. So if you find such a construction for any r, then you can use the previous construction, so like this one. So you take transversal design for the R element subsets, and then plug in the small construction. So this is the goal and hope that there is such a construction, not only for k equals 5, but for any k. But we were not able to find it. It's getting too complicated. So what do we know until now? We have upper bound for 3, k equals 3, 4, and I call this a theorem again, that we have this conjectured upper bound. It's easy to calculate that if it works, if you have a small design, then we can construct this much, but it's missing. So we didn't prove this because there is a little conjecture which is needed. But after that, we published this paper. We started to work with Zsolt-Tuza, and we found a random construction. So it is true, but it would be still interesting to find a real construction, because random is It's a very good thing, very useful, but it's somehow no one feels it a complete solution. So now I start to speak about the lower bounds. Let me start with the complementing version of Turan's theorem. I hope most of you know Turan's theorem, but this is the complementing one, which means that if in a graph there are no k vertices, that there is no edge between, so an empty k set, then it must have at least this many. I'm sorry. It must have at least that many edges as this graph has. So many complete disjoint complete graphs. Again, here the number of classes is k minus 1. So so the same idea what I used before, that if you have a k element set, then two of them must be in the same class, and it cannot be empty. So this construction, in this construction, you don't have an empty k element subset. So now I am speaking now only a graph, so nothing, no subsets, just similar. But we need a stronger version of Turan's theorem, namely if we have less than the minimum, then so we have less number of edges than in this picture, then we know from Turan's theorem, we know that there is an empty k tuple, k element subset. But if we have say 10 less, so this number of edges minus 10 edges, then how many empty k element subsets we have? So this was answered by theorem of Lovász and Simonovic. It's called saturated because they formulated in the usual sense that then the Turan theorem is in the form that if you have what is the maximum number of edges without a complete k tuple, and then they said it's saturated, so we have more edges than this, and we know how many more, then there will be many k tuples. But here we are speaking about a complement, so empty sets when it's smaller. So this is the number of edges in the construction. Yeah, n choose 2, and we have k minus 1 classes. So this is number, and we have, so this is the minimum in the complementing Turan theorem, but we have c times n edges less. So how many copies of empty k tuples we have? And this is the answer. If C is not very big, then we have at least this many empty k sets. So using this result, we were able to prove with Badakhshian this lower bound, this is different from the conjecture, so it's weaker. But the difference is very small. So this was the conjecture, the constant the coefficient here for in the conjecture, and we had here, and the difference is really very small because it's 2 over k to the 5th power approximately. So it's really very small, but still, we didn't get yet the exact value which matches the construction. So if k is 3, then the difference is 1 over 24th. And I will now again concentrate on the case k equals 3. And first I show the proof of this theorem, so the weaker lower bound for k equals 3. So k equals 3, this is, oh, I didn't tell. So this is the conjecture, and this is this value, 1 over 3. And so I want to prove only this coefficient first. And so this is what we want to prove, that if a set of edges and a set of 3-element subsets altogether form a dominating set, then the sum of the sizes is 1 over 3 times n squared. Now some elementary inequalities. So if you count the 3-element sets, then so these are 3-element sets, and for every edge, you can add 1 point to get a 3-element set. They are covered by this edge. So this m minus 2, because this has an edge has 2 elements, so m minus 2 other elements you can choose. And these ones which are covered by H and E. So we need this at least n choose 3, because we want to dominate every 3-element sets. And if if we count the 2-element sets, then every 3-element set has 3 subsets with 2 elements, and these are the 2-element sets, and they must cover all 2-element sets. So it's more than n over n choose 2. So these are the basic inequalities what we can use later. So suppose that the pair is optimal, then H is quadratic. So if we don't suppose that it's an optimal family, then it could be cubic, of course. But since we know that the sum of these two was, by the construction, it was less than a constant term n squared, so this must be quadratic in the optimal one. And it was on the previous page, and divide by n minus 2, we get this inequality, which implies, so this is quadratic and it's divided by n minus 2, so this is linear. So this can be pushed into the little o n squared. So we can forget about this, and E is at least 1 over 6 times n squared. So remember, I want to improve this. So this is trivial. I didn't use anything until now. But if we use the Lovász-Simonovic theorem, we can improve this 1/6. So suppose that h is more than this value, then we know that E, I'm sorry. So if h is more than, here we have 1/6 for E. And if this is at least this one, then we add up the coefficients 1/6 and 1/4 minus epsilon, which is 5/12 minus epsilon, which is more than 1/3, and we wanted to prove 1/3 first, right? And so then we are done. So we can suppose that this is smaller. H is smaller than this value, and now we try to use Lovász-Simonovic theorem, because in this case the number of 3-element sets is the minimum. The empty set here. So the minimum is n²/4. This time this. So this is a little bit smaller because of the 2 epsilon. So we by Lovász-Simonovic theorem we have more empty triangles because it's smaller than the minimum. And so this is the C. I repeated it here. So when C is this one, and then when C has to be 1, I show you again. Yeah. So the minimum minus C times n when C is less than this one, in our case, is 1/2. So the number of edges is at least, so the number of empty triangles is less than this one. Then the number of, is this one. And so we arrive to this lemma that E, the number of edges, should be more than n²/4. So I told you, remember, that it was 1/6 without Lovász-Simonovic, and now we got 1/4, which is better. And in a moment, I will use this form of the lemma. I multiplied it with 2/3. Why? Because we had this trivial inequality. So one of the first one when we counted the 2-element subsets, and this divided by 1/3. So this was this one 3 times h is more than n choose 2, and it divided by 3. So we had which is this side is 1/6 times n², and so we add this one and this one. This is the goal. That is 2/3, 1/3 is E exactly. So 1, and here we have 1. So we add up 1/6 and 1/6 again is 1/3. So now we we obtained 1/3. Time is fine. If you are not very tired, no, it's getting harder, because we have to use something more if we want to improve this. You remember we wanted to have actually 3/8. And at the first step, I don't want to give the full proof at once, but step by step. So now I will only improve the constant a little bit. So this one, 7/20, which is more than 1/3, but less than the conjectured 3/8. And we have to use this theorem of Rouget and Semeridi, which was actually the first application of Semeridi's regularity lemma. I don't know how much people know regularity lemma. Not really. Okay, it's not important. It's not needed. But you probably heard about the regularity lemma, just the words, yeah. And so now we are speaking about a graph only, and the condition is that every edge of the graph is exactly in one triangle. Now we don't have 3-element sets. It's just triangle from the edges of the graph. And so why it will be useful? Because here we will have edges forming from the 3-element sets, and it always true that every edge that every edge is in a triangle automatically. So when we want to use the theorem, we have to only have the property that two triangles don't meet in an edge, the two 3-element sets, because they will be 3-element sets later. Yeah. So recall that we used this inequality in this form, and we added 2/3 of E, which we had in the lemma, which was independent of anything. So we had that the size of E is at least 1/4 using the Lovász-Simonovich theorem. And so what we have, no. So this is what we want to prove now. Then multiply it by 2/5, we obtain this inequality. The 2/5 times E plus H is at least 1/5 times n squared. And so then the suitable multiple will be 3/3. So we add 3/3 of this inequality. This was the lemma. 3/3, and then we obtain E here and H here, because here we don't have H. And so we actually have 1/5 from here, and 3/5 times this 1/4. And if you calculate, this is 7/20. So this is what we need to prove this lower bound, 5/2. We had 3 before. How to reduce it? That's the question. Of course, asymptotically, we want to prove. So the little o, n squared are not considered. It's not important. And so the basic idea is that we make two classes out of the three element sets. Namely, the ones which are meet with another triangle, other three element set in two elements. So like that. And H2, oh, sorry. This is H2 when they have another one, and H1 which is alone. It might have a common element, but not a pair of elements. So no common edge. So in this way we partition the class of three element sets. A small definition: the shadow of a family is if you delete one element from each member, so you get two element sets. So these are the edges which are obtained from the three element sets. So it's actually a graph. And this is the first claim, that of course this is just completely trivial, because each edge has to be either here or in one of the members, and I just took it into two parts. So the size of the, so these are sigma h is the set of pairs contained in one three element set, and I just made it two part, and they all together they have to cover all two element sets, so this inequality must hold. Now this is the second claim. Remember, this is our miraculous number 5/2 instead of the 3. So I want to show this, that so we have a set of three element sets in such a way that everyone has another one touching altogether in two elements. And the claim is that it cannot have more than 5/2 times the number of sets in the number of edges, which are subsets of these three element sets. And without a formal proof, we have in this picture, so this three element set and this three element set, they have a common edge. So they could be in H2. And what is the number, the three elements? Two sets and 5 edges. So in this case we have equality, because this is 2 and this is 5. But what happens if we add one more? The other one, it has to touch one of the previous ones in one edge. So out of the 3 new edges, one is already used. So we added one three element set and only two element sets. So 2 is smaller than 5/2. So this is why here the ratio is better. So then this is the best, when only it can be infinite because we repeat this many times disjointly, then we can have exactly 5/2 times. But if we have always more, then it will be smaller. Now we had claim 1, claim 2, claim 3, that now we are speaking about H1. So these are the 3-element sets which don't have another 3-element set with 2 common edges. But this is, if you take the 2-element parts, that will be a graph which is obtained from 3-element sets which form triangles actually in the graph, edge disjoint triangles. And this is exactly the condition of Ruja-Semmelweis theorem, that every edge is from here is in a triangle because it's a subset of a triangle, and cannot be used twice because of the definition of H1. So I replaced here. No, so this is what we. No, I'm sorry. I jumped over the calculations a little bit. Yeah. So in this inequality, this is negligible because it satisfies Ruja-Semmelweis theorem. So the number of edges is little o n squared. So we can forget about this. And here we can replace this by this. And so we obtain from this one, this is kind of 0. And instead of this, we have this. And we obtained, and I showed you at the beginning of this trial of proof that we need to prove this, and if we have this, then we obtain the 7/20th. Now I show a general, so a generalization of this idea, which is a little bit more complicated. So now take S to be a fixed integer, and then we will prove this lower bound. Why is this good? Because if S is large, very large, constant but very large, then it will be very close to 3/8. So we can prove 3/8 minus epsilon for any epsilon, and then it proves 3/8 what was conjectured. So now we have a new partition, namely is an upper index S, if you can see. And so H1 is the set of those 3-element sets which have no intersection with S-1 other members. So at most S-2 members only, and H2 which have at least S-1. So remember, when S was 2, it meant it does not have an intersection with any other. So it's 2 with one other member. And this H2 was that it has another member with common edge. So recall the claims, because the proof was based on these three claims. And what should we get now here instead? And I will not carry out the details afterward. We have seen that these were sufficient to prove. So what do we? So now I replaced H1 by H1S, HS2, and this is again trivial, because it's just the same thing that we have we have here all together. We have all the two-element subsets of the three-element sets, and plus this, every edge should be covered either by itself or by one of the things. So this is true again. So it's no difference, no novelty here. So this was claim 2. I replaced this by S, but if we have S, then we have a new claim that we have this constant, which is smaller, of course. It's a little bit more than 2. So we started, the trivial coefficient was here 3, and then we reduced it 5/2. And we can reduce it even more. And this is the new claim. And again, this is the case where we have equality. S three-element sets sitting on one two-element set. Then, so the number of three-element set is S, and the number of two-element subsets will be 2S plus 1. So in this case, we have equality. But if we add a new one, it can give only two new edges, which is less than this one. So it is still, it will be better than this ratio. So we improved claim 2. And now it would be, after replacing this by H1S, it would say that it satisfies the conditions of Rural-Semirady theorem, but it's not true, of course, because they cover one edge many times, so it's not true. But what we can try is to partition this family of three-element sets. And so this is the new claim 3, that this one can be partitioned into many subfamilies in such a way that every one out of these satisfies the condition of the Rural-Semirady theorem, that the members of this, I mean in the H, don't have a common two-element set. So, and I will prove this, and this constant, I show how we got this strange constant. Here it is very important that this is independent on n and anything else. So it's just a constant. And so if this one now satisfies this family, the three elements, the sigma, the shadow, satisfies the conditions of the Rural-Semirady theorem, then we know that the size is little o n squared. But we have a finite number of them. They all are little o n squared. Then altogether they will be at most less than quadratic. So this is important, that this is a constant here. And now I prove this claim. Define a graph where the vertices are the three-element sets in here, our target system of three-element sets. And two vertices are adjacent if the corresponding three-element sets have a common two-element set. So they are attached to each other with one edge. And then in this graph, what is the maximum degree in this graph? So this is a vertex in this graph, and so our question is that how many triangles can be adjacent in the graph to this one. But adjacent to a triangle, another triangle is adjacent to this triangle if they have a common edge. So such things are neighboring. But we said that it cannot have s minus 1. Oh, so maybe it's s minus 3. I don't know. Okay, so we cannot in this family we suppose that no edge is used s minus 1 times, and so then if we have s minus 2 such, then we have s minus 1. Okay, so this should be s minus 3. I just wrote it today, and so then we can replace 2 by 3 actually, but it makes no difference. So it is and for all 3 edges of the 3-element set, we can have this many neighbors. So I think it's 3 is the correct one, but if we write 2, it's still true. So it's not incorrect if I made a mistake here. Sorry. Yeah. So we have how many neighbors we can have? 3 times s minus, probably 3, not 2. And now we use, so this is it. So the maximum degree in this new graph is at most 3 times s minus 2 or 3. And Brooks' theorem, I hope it is known. In a graph, if, in every graph, the chromatic number is upper bounded by the maximum degree plus 1. Actually, it's stronger. Brooks' theorem is somewhat stronger, that this equality holds only where we have a odd circle, because then the chromatic number is 2. The chromatic number is 3, but the maximum degree is 2. And the other example with equality is the complete graph. It's easy to see. Then you have equality. Otherwise, it's less than delta, so you don't need this one. But in our case, it doesn't matter. So this, we know that this is the maximum degree plus 1 is this. So we know that the chromatic number of this new graph is bounded by this number. And now distribute, so they are colored. They can be, the graph of 3-element sets can be colored. So now I go back to the original things, that instead of the vertices, now I am speaking about the the three-element sets, and they can be colored with so many colors, which means that in one color classes, you remember that two such three-element sets were adjacent if they had a common edge. But if they are in one color class, then they don't have a common edge. So it means that they satisfy the condition of the Ruzha-Semelides theorem. We need this many color classes, so we need at least so many such sets. But then, if we have so many, then we can say that they satisfy the Ruzha-Semelides theorem. And so they all have here, they are all negligible. I mean, the sigma. Their sigmas, the shadows are all negligible. And I don't continue the calculation because it's the same as in the case of s equals 2. So the crucial points were these claims 1, 2, 3, and so we generalized it properly. So it means, yeah, I just wrote what I said before. The end of the proof of this claim 3, new claim 3. And this goes further. So now I was speaking about only when k is 3. So we reached the conjectured bound, but with Jolt-Tuza, we were able to do generalize this for k element sets also. So we actually proved the conjecture we stated with Badakhshian. But we had to use a more general theorem than the Ruzha-Semelides theorem because it was only about triangles, three-element sets, and here we have something like complete K graphs. And so this is the graph removal lemma, where we have m vertices, and if the yeah, so this is a small graph. We give, say, K4. Just give a small graph, a given one, with m vertices. So in general, because this is it has m elements, so the total number is n choose m of the copies, and so if it's really smaller than the total number, so it's some very weak system, so it's little o of the total possible number, then if we can delete only a few edges, so less than n squared edges, to kill all the copies. So this is a very this itself is not a deep theorem, but it's based on the regularity lemma, famous regularity lemma. So it So this is also very deep, and you have to remember that n has to be very, very big to state anything like that. So time is over. So we settled this one and this one. So what happens if we take 3, L to be 3? Even in this case, it's hopeless. Why? Because you remember that the basic theorem we attacked these things was Turan theorem. I mean the lower bound. I am speaking of lower bound here. The construction we didn't really try. It might work in this general case, but the lower bound. And so Turan theorem, so this was asked by Turan in 45, that we take family of 3-element sets. What is the maximum number of 3-element subsets, avoiding this one, where 4 elements and all 4 3-elements are chosen. So this is avoided. Then what is the maximum number? And this problem is still unsolved. To make the importance clear, that it's very, very old. And Erdős used to offer prizes, money prizes for solving problems, but always only his problems. This was the only exception where he offered $1,000 for the solution, even the asymptotic solution, which should be 5/9. And it is, people go closer and closer, but it's unsolved. So, again, something wrong with this computer. So thank you for attention. Спасибо за внимание.
Спасибо. Any questions? Вопросы? Можно на разных языках, можно по-русски.
Not Hindi.
For the first problem about this domination number, what is the complete list of known results? Maybe I didn't catch it.
Sorry?
Полный список результатов. What is the complete list of known results?
In this problem?
Yes.
Yeah. I made it very historically.
Yes.
So I made theorems which were in our first paper.
Uh-huh.
And in the second paper, which is under works, everything is solved. So, I mean, not everything. Yeah. So this was trivial, and in the second paper with Tuza, we solved asymptotically this one completely, both the lower bound and the upper bound. So this is hopeless.